Good morning, ladies and gentlemen. My name is Marcin Ruta, and in today's webinar I would like to provide you introduction to arc flash risk assessment. So let's get started. What we're going to talk today. What is arc flash? Why it happens? What are the legal requirements or standard norms? And a brief about the arc flash analysis itself. So what is it? I think it's easier to show you than to explain. Of course, we'll do it later. This is the video from the Dunstra lab from Eton Hengelo, where I used to work, and that's 25 kiloamps half-second test. And I think it's straightforward. So we can see that the doors were closed, that there's a lot of energy being released, a lot of small sparks flying all over, and some minor things. And this is done in the control environment. And if I remember, that was something 25 kiloamps half second. This leads to something between 18 to 26 calories. 28 depends how we use the electric configurations in this particular case. So the same thing they did. I have a recording in the live. That's how it looks.
Whoa.
So that's the same. I encourage you, if there will be a chance, to go to see it. It's very nice. And by definition, and we take it from NFP 70E, didn't change. When we talk about the arc flash, we talk about the arc flash hazard, and that's a source of possible injury or damage to health associated with the release of energy. So more or less that's what we saw before on the video. Important note is that if everything is under normal operating conditions, so we are not interacting, but everything is guarded and closed, properly maintained, the likelihood of arc flash happening is very low. So that's what we call normal operations. And to put it into the pieces, what you can expect. So we focus mainly, when talking about arc flash, about the thermal energy, because the arc can reach up to 19,400 degrees of Celsius. That's a lot. In comparison, when to get second degree or third degree level, you need 96 degrees Celsius for 100 milliseconds. That's it. So we need something between us. And the arc itself, it caused the copper to evaporate with coefficient of 67,000 times. So let's say it's from 1 liter of copper, which will never happen, but theoretically we get 67,000 liters of gas, so that's a lot. And this created a pressure wave, which was opening those doors that we saw in the video. The pressure wave can be so high that it can throw away grown men on a few meters, but that's rarely to happen. We can also see intense light, and how intense, something like 12 million lux, which is in comparison, if you look directly into the sun, it's 100,000 lux, so that's 120 times more, and it can create a temporary blinding. You can also hear sound wave, not maybe here because it can reach 160 decibels, and that's a lot. Above 140 we can expect air damage. And the small particles that you saw, there was solid particles and molten particles flying all over. So they are not deadly, but they are not, you need to be unlucky to, for example, be hit into the eye. And one thing related with arc, there's also hot air expansion. And hot air itself is dangerous because you can inhale it and have lungs damage. And this influences how we design PPE. And the last thing, we have a toxic fume and gases. And that's a side effect of having arc in the panel or in switchgear. That's how we build switchgears. A lot of insulation materials, a lot of, let's say, plastic and things like this is starting to burn. And that's why we have a lot of fire, a lot of fumes. So why it happens? In practice, and as usual, it is human error. But it's not like 99%, it's more like 20-30% is directly human error, direct one. However, human error is also hidden in other points. Like we can have a wrong working culture, wrong tools, so someone selected it. We have installation quality issues like this or this. This is not the fuse, this is a copper bar for someone who is not technical, and this is very dangerous. We can have exposed electrical parts, we can have a water, dust, etc. Corrosion and loose connections caused, for example, by overheating, or mechanical damage, like here on isolator. We can have by over voltage, we can have a damage to cables. We can have animals, vermin, depends where you are located. Different, like we have rats, mouses mostly, but in other places like termites. Earthquakes, water flood, fires, those are external things which we don't really control. And when we talk about the arc flash, let's say 99 on 100 cases, there will be a damage to equipment. So we are not focusing really on protecting equipment most of the time. We are focusing on protecting human life and safety, because eventually there will be a damage to equipment. There are some solutions to prevent it, but I will talk about it later. But as I said, 99 cases on 100, there will be a damage because it will escalate to fire. Maybe we can have a fire extinguishing system, which is nice, but there will be a damage at the point where it happens. It can end up like this. Main busbar connection is burned completely to remove. This section is completely to replace. So damage will be there. It can escalate to the big fires on the whole facility. Depends what we are doing. Like here, there was a furniture plant, I believe, and it was completely burned by electrical fault, which in practice means arcing electrical fault, because electrical fault itself shouldn't cause the fire. Cost 60 million euro. And the same similar thing, Ocado warehouse in Andover in UK, where they had also fault coming from battery charging unit, which burned whole factory at the end, and it was 100 million. But interesting point was that they put the price on firefighting, and that was interesting because I never saw it before. 152,000 pounds. So whatever it happens here is actually cheaper to comply, to try to minimize the risk. Of course this can happen, but we don't want anyone to be hurt. Of course we talk about the human safety, so we talk about the body injuries, and ISA, which is International Social Security Association, made a very nice guide also, which you can find it on internet, but they did review the 61 or 60 medical cases from Germany to find out how the injuries are spreading. So that's not a big surprise that you can see hands, you can see head, especially when you don't wear PPE. That's how it looks like. But torso and legs, this is the biggest surface, and this is the most deadly area that actually you can catch. So if you have a full body burns, this surface is actually the most important one to protect. So warning, because there will be some pictures. That's how it looks like. So that's the full body burns, very dangerous thing to have and to cure. Some hands damage, legs damage. That's something you can see actually that it's not something easy to cure even. You survive the accident, but it's not that you recover 100%. I found some recordings. So that was actually recorded by accident, a news station. And what they do, they have PPE almost properly wear, and I think they didn't just expect that this arc will travel so far. But generally what they do in the correct way, and it happens. That was the video that I put on the LinkedIn, where you actually can see people inspecting something, doing some strange things. But I think if you look closely, I don't know if they have flame retardant or arc rated equipment, but this man has a face shield. I think he has also gloves. This one doesn't. So I don't know how it ended up, but it's hard to find recordings and reports on such accidents from legal point of view. So I will now talk a bit more European and then US, because now we have in Europe we have General Union Council Directive, and it's an 89391, which in general way just say the responsibility for risk assessment is on the employer side. Then we go to EN 5010, which is harmonized in each country, and this is operation of electrical installations, and this contains annex of B6 of arc hazard, and it's harmonized in multiple countries, sometimes in different way, sometimes one-to-one. So it depends on the country. I know is Netherlands has it, Belgium has it, somehow UK, Germany, in Poland even we have it. So the legal requirements are there. We have ISC 61482, which is the guide for protective equipment. However, this is just the guide, not really to how to select, just reference, but how to test equipment, how to test our clothes, our equipment that we use against arcs. And there are two methods for it. I'll talk about it later. Then we go to NFPA 70, which is a handbook of electrical safety, and this is what mainly is used in US, so let's say in America, because it is also harmonized in Australia, Canada, and this is worldwide actually used. Then this reference as one of the method IEEE 1584. This is technical standard international worldwide for arc flash calculations. So it actually doesn't have much common with NFPA, just the origin of it is coming from US. And then we have in Europe, then we have DGUV 2003077. That was German approach for thermal hazard and a guide for arc flash calculation to address box method test, because we have two methods of testing equipment, and I will explain a bit more later. And then with a bunch of support standards that we can use around the calculations, like for the marine and so on. What are the consequences? So the best one is to find in UK and US because they're reporting very well. So at this moment we have a Van Dreckle Corpus 2019, a recent one, $300,000 fine for multiple violations including arc flash, so not the only one. But AMA-LG in UK in 2015 they had an accident 11 kV cable. So the crew that was digging or making something with the traffic lights, they supposed to drill in, and they drill into the 11 kV cable. It was serious injuries. So the AMA was fined £600,000 at that time, quite a lot. I think UK changed the way how they fine companies against the turnover. In January it's still under investigation on the Equinor, so I think it's from Statoil. On one of the platforms there was an accident, and now it's under investigation. The Atomic Weapon Establishment in UK also was fined £660,000 for near miss on arc flash, so that's quite a lot. And just to mention that anything we do around it will be much cheaper than those fines. So doing arc flash assessment, to comply with all this, provide PPE, it is cheaper than all those fines and accidents itself. And when we talk about the cost of accidents, of course we have a life loss, you can have a health loss. Hard to put a price on it. I think in US they specify it's between $5 to $15 million, but it depends how you go with the social costs. We also have equipment damage, we can have a repair cost, we can have a power loss related with the production costs, we have a social cost, so it depends how we as a society approach health and safety and medical treatment costs. It depends on the country, of course. Insurance rate increase, that's straightforward, and reputation loss. That is why it's very hard to find any videos or reports. No one would like to show it. From accident statistics, because it is happening, it's not that we don't have it, we have it. In Eurostat 2017 we don't trace it very well as an arc flash, it's one bunch as far as I could find, but it was above 70,000 accidents, which I believe with electrical voltage it was a big part of it. But just to put in the comparison, in US when they track it much better, in 2017 they have over 2,000 accidents, electrical accidents, from which half of it was arc flash burns, specifically mentioned. So quite a lot, and 136 people died. So it's not that it's not happening, and usually the consequences are quite big. And now I will briefly say a bit more about the arc flash analysis itself. So I don't want to keep it too technical, but from overview point of view, if someone is from EHS or health and safety or something related, you will probably be aware about the hierarchy of controls. And NFPA has this actually inside. You can find it, and it's identifying the methods of controls from most effective to least effective. And we start from elimination, of course, elimination of the hazard, so you can lock out, tag out, arc quenching device, no live work. You can have a substitution, so we can change the voltage, but it's not practical. Maybe build arc resistant switchgear. Awareness, I treat it as arc flash labels, but what we do now is also part of it. Engineering controls, so isolate people, put some barriers, do remote operation. Administrative controls, so electrical safety plan, nice to have. And I would say, even if this is not legally required in your country or your place, it's still nice to have it because it makes things much easier and clear. And personal protective equipment, it is PPE, this is the last line of defense. We need to have it, so we did everything. And we don't, of course, want to put people into PPE and send them somewhere else to work where it's dangerous. But it has to be also selected based on proper arc flash incident energy or method, whatever, but it has to be selected based on something. And I like to add to it identification. Whatever we'll try to do, we'd like to know what the level of hazard is. So before we start any elimination, etc., it's better to know your numbers. And to know your numbers, you need to go through usually NFPA 70, IEEE 1584. Those are main things. Most of the 99 on 100 cases I will do on IEEE 1584. If we are outside of the boundary of the equation, and that's something which I have to mention now, how far we have to go with this analysis. So from transmission level we can go down, but that's in EPRI and OSHA and ARCPRO sometimes used. So that's if we go from high voltage, medium voltage system down to 15 kV. From 15 kV down to low voltage system, we use IEEE 1584. And low voltage system means, in practical way, most of the time we do it down to 63 amp protection level. But in IEEE is specified as 2000 amp short circuit level, or at 208 volts, so in our case 230 volts. Because at this level, at this short circuit count, we can sustain arcs. So that once they initiated, they can stay there for a longer time. And below this value, usually they will disappear very, very fast. So there is no associated risk with it. But it's hard to for customers to specify something like this. So in practical way, in historical way, we usually go down to 63 amp protection level, circuit breaker level. And if there is a need for something more, then we'll do it, we'll go deeper. And as far as I know, DGUV as a German approach, it doesn't have any voltage limitations. So technically or theoretically we can apply it to every voltage level. However, I'm waiting for the field previsions and some results proving this. From analysis point of view, so let's go step by step and I'll briefly explain how it works. So of course we have the foremost side where we have to do the identify the scope of work, got some basic information, and then go through offer and things like this. So once we have this done, we start with data collection. And data collection means collecting the information from site, because usually there will be site visit. We don't focus only on paper data, we try to verify data on site to compare it or at least review it if that's actual, because there is very often difference between the paper version and what is in the field, and we need the field data. Then we create the model in software. Usually it's in software because it's easier to handle it properly and also to modify it later. So and I would say you can do it manually, you can do it by hand, but for bigger system or typical factories, it's better to do it with software. We run calculations, so as a basic is a short circuit study, selectivity study, arc flash calculation, and equipment evaluation. Equipment evaluation is just checking with the short circuit most of the time if our system is properly designed and will withstand the currents in the network. Selectivity study is just to check, or just is as a base to check if our protection is made properly, and it will be necessary for arc flash analysis later. And once we have this done, we have identified the existing situation, and that's one part of the report. Then I will review the results and provide recommendations for improvements. That's a very important step because that's part of the elimination or reduction, and we would like to adjust the model for site-specific recommendations sometimes, improve the settings of the protection relays or devices, then rerun everything, make it again, And then we have a second part of the report with recommendations. This goes into the report, all the information has to be there. It's good when the report is written in the nice way with all the recommendations in, let's say, not very technical way, so customer can understand it and know what they have to do. Of course, you have help with it, but depends on the company, of course. Then big part is ArcFast training. So now depends where you are. Sometimes like in US, Canada, this is combined with electrical safety training and can take 1 to 3 days. In Europe, we have a little bit different because electrical safety training is all part in the qualification, all part in like special authorized bodies would do it. So I focus purely on ArcFast in this case. And sometimes there is a report presentation to explain a bit more or discuss the findings of the reports, because it's very important to put emphasis on understanding of the situation. Then we do then I also help as a PPE selection support, which means it's good when the customer knows how to select the PPE at the end of our work, because otherwise everything generally means nothing then if they don't know what to do with this. And at the end we have a follow-up. So we have a model, we have everything done. Every 5 years maximum we have to update it, which means that every 5 years or every bigger modernization on site. So if we move the switchgear, change some machines, maybe updated the transformer to different one, change the protective settings, etc., then we have to update the calculations to have the real data. Once we talk about identification, we recognize 2 groups. So we have a shock hazard danger zones and ArcFast hazard danger zones, so-called ArcFast boundary. And shock hazard, they are fixed because they depend on the voltage level. So it's like for low voltage, it's usually like no touch and then 30 centimeters, 50 centimeters, depends on the country. And there is a small difference between US and European, but they more or less are the same. And we call live working zone, vicinity zone, or limited approach boundary, or restricted approach boundary in US. And so that's fixed and depends on voltage level. ArcFast boundary depends on voltage level, but there are multiple factors. And for the same panel, like this, but with different factors, then this boundary will be different, and it can be like few meters on low voltage level. So that's how it looks like. This is video by eHazard, but I like it because it's showing actually here the effect of opening the doors and arc blast. But if I like it because it's showing very nice how the arc travels, what is the reach of this ArcFast boundary, how big it can be. And we usually calculate it down to 1.2 calories per square centimeter, which is the threshold of 2nd degree burns. So what we want to achieve. So first we would like to identify the instant energy levels, so we can properly select our PPE, but also adjust our actions for elimination and reduction, and also maybe prioritize the plan for upgrades or modernization. So we have a system like this, and this is a real project. We would like to select it, so we did calculation, we know that it's 12.8 calories here. So we would like to select the set 1, 15 calories per square centimeter, and usually it comes with the ArcFast hood above 12 calories. And here at set 1 it was 40 calories at low voltage. And there is one hidden thing behind it, because you maybe see that on the low voltage we have actually higher energy on the medium voltage. And that's very common. That's because of the low voltage, it is actually more dangerous in this case. It's not logical, but that's because of how we design the systems. And also depends on the situation that ArcFast behaves a little bit different on low voltage side, or actually it behaves the same. It has almost the same arc voltage drop, which is influencing the arcing current versus short circuit current. So in practice, short circuit current, let's say if we have 100 kilo or 50 kilo amps on low voltage level, the arcing current will be can be something between 30% to 70% or something like this, and it means that it will be like 20 kilo amps. And sometimes for protective device it's so low that it doesn't see it as a fault and has increased settings, or see it as a fault but temporary, and increase the settings, and that caused the higher energies. And when I talk about the protective equipment, I said that we have ISA 61482. It has 2 methods. OpenArc and box test for testing. And everything which is NFPA relative is going to OpenArc. And box test was something which I mentioned for DGUV. So if we go with OpenArc, which means calories per square centimeters, we have a tested PPE. So we can select it based on our calculation from IEEE 1584 or based on the table method from NFPA 70E, because there are two methods of actually doing this calculation. And when we have box tested, so we then refer for DGUV. For a very long time in Europe there was no method. So we have the method for testing PPE, but we didn't have method for selecting the PPE, which is kind of strange. And this is, I think, if I built from 2015 or 12 only. ArcFlash results table, so that's generally how it looks, but you see maybe some addition because this is from SKM. Not complete table, of course, but you can see here like those are results for existing situation, existing settings, and then after improvements. And this from real project. So you actually see that there is sometimes significant difference where we can actually drop the settings and make it better. Sometimes I put it on and most of the time I put it on the single line diagram, so you can actually see it better in visual way. I think it's just the additional thing, doesn't cost me much work, so it's a nice thing to see. You directly see this color coding, and I would say it's straightforward. At the end we have to label all installation, so whatever we do, whatever the country is, it has to be in local language. If I'm in France, Germany, Turkey or whatever, we use local language to make the labels. There are some requirements, of course, for labels mentioned in FPA what has to be there, but in practice there is one thing maybe I can mention here, because there used to be a word danger and no safe PP exists. That's kind of what's happening for labels above 40 calories, and that's more historical way. It was changed, I think, 2 revisions ago. We don't have to use it, or actually no one has to use it, and instead of this I'm using word warning, and then you just can match your PPE. It's still with the red label behind it, but we don't use this text anymore unless the customer really insists from their point of view, because you can select your PPE up to 120 calories per square centimeter. So that's not really, from your risk assessment you get information that okay, you cannot select your PPE, so you cannot work on theirs. But it was a problem sometimes because you can have PPE for 70 calories, but no one really officially cannot work on this because it was written no safe PPE, in danger, don't work live. So this is change. And so now I will talk a little bit about how to mitigate and reduce the arc flash. So of course, as a base thing, we talk about the settings improvements, and that's what we have as a base. I do it in the report, part of elimination, because usually it's possible to do it and it's feasible. It's no problem. If we cannot fix it, we try to start with the active fiber optic detection. Then we can also use arc quenching devices. Depends, multiple companies do it. I used to work in Eaton, so I have it here. Internal arc classification, so we can build our switchgears on medium voltage or low voltage to be arc resistant or arc classified, which means they will keep the arc inside panel if something will happen. There is one word of information here, because this works only when the panel is closed most of the time. So if you, for example, so 9 on 10 panels or 99 on 100 on medium voltage will be internal arc classified, there is no problem. But on low voltage side there will be 1 on 100 arc resistance. So usually that's, I believe it's because it's a very nice thing to have, but if you do any maintenance, if you work on the equipment and you open something, then generally you don't have this arc classification anymore. You can also have the special trip units in the low voltage breakers, where you can actually, you just have to want to someone that you would like to have it, like it's Eaton, Siemens, Schneider, whoever has it, they should have it all, and you just have a special maintenance mode. This is called arc flash reduction maintenance switch. So it's special function in trip unit which will activate it manually and will reduce the settings so it breaker works as fast as possible, and that's just on cost on selectivity temporary. it will improve usually it will improve the situation, but you have to check it first. You can also reduce energy, not like going minimum, but just to reach a certain level. Just the way how to improve. We can improve it by communication between the breakers, which will save us time, so the breakers will act faster. And short circuit current adjustment, this is a specific topic because it doesn't always lead to better results, and that's counterintuitive when it comes to arc flash, because lower short circuit current actually can be much worse situation. So it's not only maximum currents that we take into account, we actually take into account minimum currents also, short circuit currents. Lockout, tagout, I think most of the companies know nowadays. Remote operation SCADA system, so when we can operate remotely something like breakers. So the problem is still there, hazard is still there, but we are not there. So kind of solve the situation. And also some other specific topics. And from my side, that's all for today, and I hope you enjoy it. And now it's time for questions. Thank you very much.